use. Okay. So we consider the mean square for treatments. It's just the average. Okay. We know that SSB will be the total variability between treatments. Now we not only interested on the total variability, we also want to care about the mean or the average of the total variability due to treatment. Okay, we consider MHB equals to the sum square of differences over the degree of freedom k and minus 1. K because we have k root. The average of the variability due to the errors or the mean square errors, MHE, equals to the total variability divided by the degree of freedom. Kn minus 1 because we have the total number of observations will be nk minus the number of groups we have k. Okay. And lastly, we accepted the next few results. Firstly, if we consider the mean E of SSB is equals to two terms Kn minus 1 sigma square plus n sum of 2i square. It's not difficult to prove, but of course it's the hour of the scope of the lessons. And I introduced to you E of SSB equals to Kn minus 1 sigma square. The given two equation is really important. We use this to make the hypothesis test, to make the conclusion for our hypothesis test. Okay, let's return to the board. Sorry. 5 minutes, okay? Let's rest in 5 minutes. I will return. Sorry, I have not good health today. Okay, I return. Okay, firstly, let I introduce you the definition. We have the estimator theta half is called an unbiased estimator of theta if and only if the mean of theta half is exactly equals to theta. Okay. Okay. So, for example, actually, we have seen the unbiased estimator many times. For example, we always consider S bar as the estimator, as the point estimate of the population mean mu. Okay, because we have E of S bar, the mean of S bar always equals to mu. Right? Do you remember? Because S bar equals to the sum of Si over n. So if Si has the mean E of Si equals to mu. So E of S bar always equals to mu. Okay, that's the reason why we always choose S bar to estimate for mu. Okay, or we always choose S square, which is the sample variances to estimate for sigma square, where S square equals to sum of Si minus S bar square over n minus 1. Okay. In that case, we said that we have an unbiased estimator. Okay. This definition is important in our case because return to our slides. Consider the first equations and the second equation. Sorry. We have E of SSB. We have equation 1. We have E mean of SSB equals to K minus 1 sigma square plus n sum of tau I square. I from 1 to K. And the second equation, we have E of SSE equals to K n minus 1 sigma square. Okay, so let's see if we can recognize that we can start from equation 2. Equation 2 equivalent to if I divide K n minus 1 from the left and the right, so we have E of SSE over K n minus 1 equals to sigma square. Okay. Equivalently, we have E of MSE equals to sigma square. Right. So it means that if the mean of the estimator exactly equals to the variable, equals to the parameter, it means that we have MSE always unbiased estimator of sigma square. Okay, MSE is always an unbiased estimator of sigma square. Then equation 1, the same equation 1. If I divide the left and the right by k minus 1, so we have E of SSB over k minus 1 equals to sigma square plus n sum of tau I square over k minus 1, right? So now we can recognize that if H0 is true, remember that in hypothesis test, always the first step, the null hypothesis H0 is assumed to be true. Okay, we always assume H0 is to be true. Okay, and using the first step, if H0 is true, what does it mean? It means that tau 1 equals to tau 2 equals to tau k and equals to 0. All of the treatment effects are 0. If the treatment effects equals to 0, it means that the second term here, the constant term here, this will be 0, right? So this term will be 0. So if S0 is true, then we have E of SSB over k minus 1, we have MSB will exactly equals to sigma square. So it means that in case S0 is true, then E of MSB is exactly equals to sigma square. Hence, MSB also an unbiased estimator of sigma square. Okay, so we see that we have two sample estimator. They are the same estimate for sigma square, but MSE is always an unbiased estimator of sigma square. It means that you always able to use MSE as the estimate of sigma square. Okay, we don't need the hypothesis H0. So in case that H0 is true, then MSB also the estimate of sigma square. Okay, so now let us remind you, what is the target in hypothesis test? In hypothesis test, we always need two steps. Step 1, we need to define statistical we always need to define a hypothesis test. We always need the hypothesis statistic, right? And then step 2, we need to define or rejected regions. The test statistic, the rejected regions. Okay, if we able to answer for step 1 and step 2, So we able to answer for the question whether we should readjust S0 or not. Okay. But step 1 and step 2, basing on the fact that S0 is assumed to be true. Okay. Now, to answer for the question about the test statistic and rejected regions, we need to know when will we reject S0. We just know that in case S0 is true, then both of SSB and SSB, MSB and MSE are the unbiased estimator of sigma square. They have two estimators to estimate for the same parameter of sigma square. Now we want to answer for the question, when will we reject S0 and when we won't reject S0. When we should reject S0. Remember that in Anova model, we assume that the treatment will be the main effect, and all of the other effects will be considered as the random variable. So if our model is a good choice, means that we want the total variability due to the error should be small, right? And the variability due to the treatment should be large. Agree? We reject S0. We reject S0 means that there is the effect of between treatments. It means that the between treatments indicated by SSB, and the average will be MSB. So it means that we want MSB is as large as possible, and we want that MSE must be as small as possible, right? So the target is that we should reject S0. We should reject S0. Reject S0 means that there is the differences between treatments. There is the differences between treatment. It means that we want MSB is large and MSE is small. Why? Here, look at this equation. If we reject S0, it means that there exists at least one tau I different to 0. If tau I different to 0, it means that all of this constant term will be greater than 0, right? So if this term is as large as possible, if it's very large, so we have more confidence that there's so many terms of tau I different to 0. It means that we should reject S0, right? And in case that this term is very small, so it means that we have lower confidence that there is this tau I different to 0. It means that we won't reject S0. So in general, we see that because of this equation, because both of MSB and MSE will equal to sigma square,